Okay, here is a lesson on AC theory. It follows on from probably all the electricity topics we've done, so it's probably worth having a look at those first before we get started with this one. However, I'm sure you're aware that coming through the mains electricity, we don't have DC, but we have AC current. What does AC stand for? It stands for alternating current. And so what that means is that rather than having a nice steady current like a battery, what we have here is a series of, well actually, its current goes from positive to negative, positive to negative, and that takes place constantly, back and forth, coming through the plugs. Some facts are that the frequency runs at 50 Hertz, 50 Hertz is mains, and also we know that the voltage that's coming through mains is 230 volts. Current, voltage, both of these behave in a similar way. They both have a sinusoidal pattern going from positive value to a negative value. Positive to the negative, both equal in quantity, and they both go around a maximum value. The maximum value we call V0, or indeed I0, and sine of omega t. Omega t, when you multiply them together, gives you an angle, in effect. So you can imagine this as being an angle. So we're going to vary between the sine is positive 1 or minus 1 multiplied by this scalar, which gives us our initial starting voltage. Good, so that's what the voltage is, and that's what the current is coming through our systems. Now there's a huge discussion as to why, well there's a good reason as to why we have AC coming through, and I will quickly go through, now we have the facts down, why we use AC. Well, generators work and produce a certain electricity for us, and then that's taken into the national grid, which carries, these are pylons by the way, that carries the electricity through to our homes. Now we want to try and reduce the power loss in these cables, because these are huge distances they cover. And the power lost is going to be the current squared times by the resistance. So if somehow we can try and reduce the current as much as possible, then the power loss will go down equally as much. Well, actually not equally as much, sorry, it's going to be greatly reduced because it's an I squared factor. So how do you manage to reduce the current? Well, if you're able to step up the voltage and transform the voltage up, then the current will come down. And how that's achieved is through a transformer, and there's a whole video on transformer theory which you can watch if you're not feeling too confident about the theory. So you use a transformer which steps up the voltage, hence we have a step up, which in turn steps down the current, which means there's reduced power loss. And when that gets through to our homes, of course, you need the opposite to take place, because you don't want to take through a huge voltage into your home. So you step down the voltage and up the current again in a step down transformer. So, why AC? Well, transformers only work with AC. Only work with AC, alternating current. And again, there's a whole other video as to why that is the case, but essentially it's because you need a changing magnetic field in order to cause induction from one coil to the next. Okay, I think there's some history that Edison tried to make a distribution system that's based on DC and lost most of the electricity en route with the power loss. So this is a system they use around the world today at different voltages, other than the one we mentioned here, but nonetheless, this is the idea. So that means, coming back, we have, in effect, our circuits run with AC. I'm going to do a basic circuit here, and there you go. Let's say I've got 2 ohms running there, and I have 10 volts AC. And I say 10 volts, let's call it equivalent. because we know that obviously the voltage and the current is varying, but we're quite happy in describing in our homes that we have 230 volts equivalent coming through. And if we have 10 volts equivalent coming through, then that will give us 5 amps equivalent coming through this resistor, and therefore producing a power output of 60 watts for that resistor. Now when I say equivalent, it's because what we're trying to do, what we've done here is we've said this AC we've converted almost into a DC system. And of course my DC system, if I did have a DC system, I'd say current would be flowing of 5 amps and the 2 ohms, thereby giving me a output of, let me just do the sums a little bit better here, sorry. Power output is I times V, which gives me 50 watts. Apologies, 50 watts output. So how do we then, so this is my equivalent circuit of my DC circuit. So how do we work out from a sinusoidal wave what the equivalence is happening here? And if that's confusing us a little bit, then maybe I can use a mechanical analogy here, that if I had let's imagine I had a bandsaw, I'm sure you've seen these in the design technology department, and I had some wood that needed cutting. Here is my bandsaw. Let me draw that on this side. You'll see why with the analogy in a minute. So I have my bandsaw, and of course the wood. I am cutting the wood, and you can imagine that this bandsaw flowing around is a little bit like the current flowing around. Cutting the wood is like the power. Now the equivalent of my alternating current circuit, my AC, would be a jigsaw cutter, in which I have my bit of wood, jigsaw, and with the jigsaw cutter this bit moves up and down, thereby moving the saw up and down, cutting the wood. Similar to AC, it's going up and down, up and down, up and down, cutting through the wood. Power output is the cutting of the wood. The up and down is like the current. The bandsaw is cutting the wood, but this time it's a rotation, it's a continuous blade that's moving up and down, similar to the continuous current that's flowing. In both cases, I'm achieving the same outcome. So what we're trying to work out is this equivalence taking place. Good, so if we have worked out the equivalence, now let's talk about the theory as to how we achieve what the equivalent circuit will be. Okay, we talked about my current as being sinusoidal. And of course here, the average current, I'll just write average just in case we're not familiar with that notation, is going to be 0. It's going for equal amount of time above and below the line, we've got 0 amps going through. But according to our analogy here, we know it's cutting the wood. Cutting the wood is similar to the power output. So let's just take a look at the power output. In other words, it doesn't matter which way round it's going, I'm still producing power here and producing power here. In other words, I know that the power is equal to I squared R, and I know from my first instance that the current is I naught sine omega t squared R. So if I needed to draw this, for those of you who are very comfortable in maths, and now I use the power against time, I should have said time there, you'll probably realise that if you square this function, you get nothing below, but everything is above. And if I try and use the same values for time, what I have here is, I have an increasing function, decreasing, and then it increases again on the positive side, decreasing. Positive side again, decreasing, positive side, again decreasing. This should probably be a much bigger value than that shown. But nonetheless, the power output is always positive. Now this is starting to make more sense because I always get the wood is being cut. I'm not cutting the wood and then replacing the wood. It's always cutting the wood. I'm always producing a power here. But it's constantly varying. So therefore, I'm trying to look for my average power output. And my average power output is going to be equal to, well, what you notice about sine squared is that the average value for sine squared is a half. It's a half whatever the max value is. If that is my maximum value. So therefore my average is Pmax. In other words, it's going to be a half I naught squared R. Exactly what I have up here, I squared R. But this time I'm changing this factor into a half, so it's I naught squared R. So what I'm saying is now I've worked out my average power output, which implies that that's the same as my I equivalent squared times R. What we describe as the equivalent, which I know now is going to be a half the maximum value of my current times R. So my I equivalent is going to be, if I go to the I's, I naught squared divided by 2 square rooted, or indeed I naught over root 2. So the equivalence of, I'm going to draw this again, whether this is current or voltage. It's current or voltage, that doesn't mean current measured in voltage. I have this up and down, time. The equivalent value, just call it EQ, capitalize it, is going to be my maximum value divided by root 2. And that is incredibly important. Indeed, V equivalent is going to be V naught over root 2, and indeed I equivalent is going to be I naught over root 2. Good, so we could probably say, if I'm drawing the analogy back, that the jigsaw is not quite as effective as the bandsaw, but it is effective to the value of 1 over root 2, to the same value. Now, it's important here that we cover one area. Writing equivalent is not actually correct, because what we have actually done is I equivalent was actually the square root of all the I square values added together divided by however many there were, and then I square rooted it. What I did here, of course, is the half is me making an intelligent guess as to all of these added together, all these little values that I'd have, that I'd squared together, dividing by how many they were, gave me a value of a half. However, nonetheless, what I did was here, I'd squared them up, taken an average of the squared, and then square rooted it. So what I did was I square rooted the average of the squares. And working back, what we call that is, we call that the root mean squared. Or very simply, RMS. So where I've said equivalent, I should be saying the RMS, the root mean squared value. So therefore here, V naught over will be V RMS, I RMS. Okay, now there's the theory with the reason why we have RMSing. RMSing is just it's another average, but it's not actually the same as an average, because the method of operation by which I go through these means that I'm not going to come out with the average again. If I wanted to do the average, I'd have to square them, then square root them, and then take the mean to get my average I value, but that's not what I'm doing. Okay, let's try a couple of questions, because this is actually, well, no, before we go on to some questions, let's describe how we would find this on an oscilloscope, because these two topics link together. So let's work on oscilloscopes. I won't go through the operation of an oscilloscope, but what I will describe is that on the front of an oscilloscope, and it's a cathode ray oscilloscope, so that will give you an idea of how an oscilloscope works. You have a lovely screen which is evenly divided in both the Y, the X, and the Y direction. And in effect, what you should imagine is everything that's happening in the Y is a voltage, and everything that's happening in the X is a time. So what happens, well, you can have traces built up, which are showing how the voltage is varying with time. The nice thing about an oscilloscope is that you can change the sensitivity of each of these squares. And let's say, for instance, we had, I don't know, 1 millisecond per division, which you can alter yourself. And let's just imagine that we had one of these was 5 volts per division vertically. Then if I were to put a trace in, and I hope I keep this fairly constant, quite hard to draw, then I would be able to read from this trace lots of things about this wave. For instance, let's work out, first of all, the time period. Then we'll work out the frequency. Then we'll work out the peak voltage, and then we'll work out the RMS voltage, all in order. But if you think you know what's happening, hit pause, of course. Otherwise, here comes, and give it a go. Otherwise, here comes the solution. First of all, the time period. Well, we know the time period is the time it takes for this wave to go through one cycle, or indeed go from peak to peak. Peak to peak is nice and easy here because it gives me 2 divisions. I also know that I'm running at 1 millisecond per division. So that gives me 2 milliseconds as the time period. Good. Frequency. Well, delving through your knowledge of, say, year 9, you'll know that frequency is 1 over the time period, which means that's 1 over 2 milliseconds, which I know is going to be 1 over 2 over 1,000, converting this into seconds, which gives me 1,000 over 2, which gives me 500 Hertz. Excellent. Now we're going to run and work out what the value for the voltage is. Now, I'll forgive you if you've got a different value for me. However, it's really hard to work out where that starting point is. So what we usually do is we usually work out V peak to peak, which here is 1, 2, 3. And we can assume that V peak to peak divided by 2 times by 5 volts per division will give me the value. In other words, the peak to peak divided by 2 works out where that line is, that starting line. So here I have 3 divided by 2, 1.5, times by 5 gives me 7.5 volts. That's its maximum value. And VRMS, very simply, is going to be V0 divided by root 2, which gives me 7.5 divided by root 2, which gives me, and I don't have my calculator on me, so I'm going to guess something like 1.41 going to be about, what's that, 75 into 14, that's going to be about 6. 6 of those gives me 74, so it's approximately 6 volts-ish. Good. But it's quite a simple idea of an oscilloscope, how you work. You work out the number of time per divisions, multiply up by the trace, work out the number of volts per division, and multiply that up by the trace, and then work out peak to peak and RMS. Good. So, what else do we need? And the one last one, I suppose, is that coming all the way back to the beginning, I said that we're running an equivalent of 230 volts with our mains electricity, and at 50 Hertz, so therefore it's probably worth wondering what is our maximum value of mains electricity and what's the time period. So here's our time, here is V. I know that my equivalent is 230 volts, or my VRMS, should I say. And I know that I'm running at 50 Hertz, so therefore what's my peak value? What is V0? And also, what is the time period? If you think you know, hit pause. Otherwise, here comes the solution. Well, V0 divided by root 2 gives me 230. So therefore, V0 is going to be 230 by root 2, which is, to no calculator, but 1.4 is going to be something like 325, let's say. It's a nice round number. So actually we're running at 325 volts to minus 325 volts. And if the frequency, the time period is 1 over the frequency, then 1 over 50 gives me 0.02 seconds. So I know that this value here is 0.02 seconds. So that's mains electricity and how it's coming through. Right, hope that makes sense.